Now see, in our day-to-day life, we experience this thing when any object or the body or the system is heated. So from one part when it is heated, the heat will be transferred to other part also. It implies that the transfer of heat takes place in the body, in the substance, or we can say in the system. Now we have three states of the substance, or we can say matter: solid state, liquid state, and gaseous state. Okay. Now in these different states, the heat transfer takes place by different modes. In solids, the transfer of heat takes place by conduction process. In liquids, heat transfer takes place by convection method or convection process. And in atmosphere, the heat transfer takes place by radiation method. So here all these three we will discuss. Now first we think about the conduction process. Okay. So in solids, the transfer of heat takes place by conduction process. So if we take any solid substance just like a rod, then if it is heated from one end, then we experience this thing after some time, the other end is also heated. So when the transfer of heat takes place in the solids, that is due to the temperature difference between adjacent part of the solid. Now, in this particular process, the constituent particles of the solid play important role. How the heat is transferred from one part to another part. So if we think about the solid substance, now suppose if one part of it, suppose this one is the rod. Now if this particular rod is heated from this end, so the constituent particles of this rod which are in contact with the source of heat, first it will absorb the heat. Due to that, their thermal vibrations increases. Now all the constituent particles are associated with successive particles with interatomic or intermolecular forces. So if the vibrations of the constituent particles in this part increases, then the neighboring particle also gains some energy from it, and due to that their thermal vibrations also increases. So in this way, the heat given to the constituent particles which are in this particular part, or we can say in this plane, will transfer the heat to the successive constituent particles in different planes. And in this way, the heat will be transferred from one end to other end, and after some time, the other end that will be also heated one. So this is the conduction process. So in conduction process, we can say this thing: the translatory motion of the constituent particles does not take place. Conduction process, that is due to the vibrations of the constituent particles. Now let's derive the equation for the heat current. Suppose here, as shown in this figure, we take one conducting rod and its sides are perfectly insulated one. One end of the rod that is placed in the contact with the system C, which one is at higher temperature Tc, and other end of the rod that is in contact with system D, which one is at lower temperature TD. Now, here the heat will be transferred from high temperature to low temperature. Suppose here temperature of the system C that is greater than that of D, means TC is greater than TD. So from C to D, heat will be transferred through this particular rod. Okay. Now, when the thermal steady state of the rod is attained. Now, what is the meaning of thermal steady state, or we can say steady state? So, see here, what happens? The heat will enter to the rod from this particular end. And now it will be transferred to the successive parts, and finally it will leave the rod from the other end and will be transferred to this system D. So amount of heat enter to one end of the rod per unit time, and the amount of heat leaving the rod at other end per unit time, when this becomes the same one, then we can say the rod is in thermal steady state or steady state. Clear to all of you? Now, experimentally, we can observe this thing, the rate of flow of heat, which is also known as heat current. It is denoted by H as well as it is denoted by dq by dt also. So, rate of flow of heat or heat current, that directly proportional to the temperature difference between these two ends of the rod, as well as it directly proportional to the cross-sectional area of the rod, and it inversely proportional to the length of the rod. So collectively we can write H proportional to A into Tc minus Td by L. So here we have to introduce one proportionality constant. So we can write H, the heat current flowing through the rod, that is equal to Ka into Tc minus Td upon L. It is also denoted by dq by dt, where K, that is the thermal conductivity of the matter, and its unit will be joule per second meter Kelvin. If you want to prepare its dimensional formula, then for joule you can write m1 L2 T minus 2 upon for second T1, for meter L1, for Kelvin K1. So finally you will get m1 L1 T minus 3 K minus 1. So this one is the thermal conductivity. Now here we derived the equation for the rate of flow of heat or heat current through the rod. Clear to all of you? Now see, thermal conductivities of different materials are given to you in the text in table number 11.6. And here we can observe this thing. The substances for which the thermal conductivity, that is large one, we can say are very good conductor of heat. And the substances which are very good conductor of heat are also good conductor of electricity. Now, you already studied about electric current. If we think about any conductor, which one is with resistance equal to R, then if the potential difference is applied between two ends of the conductor, then the current will flow through the conductor from high potential to low potential. And we give that electric current I, that is delta V, or simply you can write V, the potential difference upon electrical resistance R. So here we can establish the analogy. Now, between two ends here, when we apply the potential difference, then electric current is constituted through the conductor. Similarly, when we take here the temperature difference between these two ends, then heat current flow through the conductor. Now see the analogy in these equations. Electrical current I, that is equal to electrical potential difference V upon the electrical resistance R. Now rewrite the equation of heat current as Tc minus Td upon L by Ka. This Ka in numerator is written as the denominator to denominator. Now see, this numerator is the temperature difference. H, that is the heat current. So the temperature difference is divided by this particular term and you are getting heat current. So here if we think about the analogy, then in this equation R is the electrical resistance, then we can say from this analogy L upon Ka, that is the thermal resistance. That is called thermal resistance. So thermal resistance, that is given by L upon Ka, and its unit that we can write Kelvin upon watt. Kelvin upon watt. Clear to all of you?